I hope everyone has been able to finish their spoken tutorial on the post processing. Please post your questions on the spoken forum as always. And a quick round of yes on the chat box will help us know how many of you are through. Okay, so as expected, many of you have already completed it. I've noticed that our guest speaker, Professor Valluri, has also joined. Good afternoon, Professor Valluri.
Shweta, I'm also here.
Oh,
yeah.
Good afternoon.
Hello, everyone. Good afternoon, Shweta. Hi, Kanan. How are you?
Happy to see you. Happy that you could join us, although it was a short notice.
No problem. No problem. Always a pleasure. I mean, the thing is, it came at the right time because I just gave a lecture for Japan on that day. so it's and it was broadly on the similar topic. So yeah.
Terrific. Do you want to? Are you displaying something?
It says that I'm not permitted to share the screen if I can get the rights.
It just removes whatever is being displayed.
Yes. It's done. Yeah. Sushant, please give the sharing rights.
I had already given the co-host permission.
Okay, thank you.
Excellent.
We are delighted to have Professor Prashant Valluri. He's a professor at University of Edinburgh at Scotland, and he works in the area of fluid mechanics. And he doesn't necessarily use OpenFOAM, but he does a lot of CFD, and some of them are released as open source as well. And Professor Valluri has been interacting with us quite a bit. He's a friend of IIT Bombay. He has given talks at IIT Bombay. He has been a PhD examiner. Some of you would like to know that he got his bachelor's degree at Batu, Lonere, and he has done amazingly well. And it's a real, in fact, when I visited Scotland, I think it was 1.5 years ago, he arranged a talk. I was happy to give a talk there on our FOSSEE and spoken tutorial projects. So really delighted to have Professor Prashant Valluri. He's going to, you can see the talk he's going to talk on introduction to stability analysis and direct numerical simulations for two-phase flows with and without phase change. And he is actively looking for people who are good in fluid mechanics, computational fluid dynamics. Over to you, Prashant.
Thank you so much, Kanan. Thank you so much. It's actually a pleasure and honor to always speak to my colleagues at IIT Bombay because I mean, number one, the reason is Bombay was the place where I was born. My father and my parents. I mean, they were working in BARC, so I was completely born and bred in Bombay. Plus, at the same time, I do have, as Karan mentioned, I do have long-standing links with IIT Bombay. One of the things was my late uncle, my mom's brother. He was the head of computer science and engineering in IIT Bombay, Professor SSSP Rao. So he passed away a few years ago. But because of that, I used to always come to IIT Bombay, especially holidays, and in the pretext of getting tutored by my uncle, but we used to play cricket all the time. Don't tell my mom about it. She'll be very angry. But anyway, so I've got a very close link with IIT Bombay. Plus, recently, one of my cousins, Abhijit Gogolapati, he's also a lecturer in aeronautics in IIT Bombay. Plus, my cousin's sister, she also leads the commercialization team there. So I've got long-standing family links. So it's always a pleasure to always interact with people from IIT Bombay. Okay, so before anything, so my talk, as Kanan mentioned, my talk is not going to be on OpenFOAM, but I'm going to be talking to you about direct numerical simulations, or CFD, as you know it, for multi-phase flows and with and without phase change. So multi-phase flows are basically a particularly challenging flows if you want to simulate. The reason is you've got two phases. You've got liquid or gas or liquid or solid or whatever you want, and combinations of them. And then each one has to be treated with utmost respect if you want to really simulate that. Okay. So what I'm going to do today is basically give you an insight into how you simulate two-phase flows. So this you can do this in open form as well. You can do this in your own solver, because some of the work I'm going to present is going to be based completely on our own solvers. So we develop our own solvers. It's on highly parallelized networks and things like that. So so while this is not concerned with open form, you can use the same principles. The fundamental principles will not change. Okay, so so quickly, the thing I would like to say is, whenever we do any sort of simulations, the first thing we need to check, the first thing we need to do is check it. That is through validation, and that is in my work, and especially for two-phase flows, we do it by means of stability analysis. And why is that? Is because if you look at any sort of a two-phase flow scenario, you've got an interface, you've got a liquid, or you've got a gas, and the interface is always disturbed. And based on how it is disturbed, you got a regime in two-phase flows. Okay, so that is a very complex thing. And to identify, so that's why I keep telling, that is the first line there, which says instabilities are the language of multi-phase flows. So multi-phase flows always speak in this language. So here, I'm sorry for the huge list of authors here. This is just a tribute to all my collaborators all over the world. You can see that I've got very strong collaboration with Rama Govindarajan as well from ICT STF Bangalore, plus all over the place. And the people indicated in blue are my PhD students, some of them ex-PhD students, some of them are current PhD students who have worked with me in the areas of two-phase flows as a part of my group. Okay, so the first thing I would do is, I would not go into CFD now, because I'm sure throughout the day you've been listening about CFD. You might be sick and tired of it. But the thing is, what I'm going to talk about is basically stability of small amplitude waves. This is the basic stuff of how to validate your CFD simulations or DNS. The reason I call them DNS, is direct numerical simulations, is because I don't use a turbulence model there. Okay, I really resolve my my domains to such an extent that I don't need to rely on any turbulence models. Okay, so so basically, this is about linear stability analysis. So the first thing is, any sort of a flow is never steady. The moment you have a flow, you turn on your tap, it's an unsteady flow. People say that, oh, you will get a steady state. It's all a joke, because you don't, you will have a quasi-steady state. It looks like you have the same constant velocity, but if you look closely, none of that is constant. You've got packets of waves that are dropping all over the place. It's a highly transient scenario. Okay, so one of the examples I would show is this formation of clouds. So if you see this, so basically, if you look at this, you've got this is atmospheric flows. Okay, and this is not two-phase. It's basically single phase. You've got air on top of the cloud, which is going at a pretty high velocity, and air at the bottom of this cloud, of this line, is going at a lower velocity. And because there is this constant interaction between the two, you get these turning waves, and these are called as the Kelvin-Helmholtz waves. So these are cat-eyed waves. Okay, so that is called as the Kelvin-Helmholtz instability. So if you have a system wherein one part of the phase competes with the other in terms of the velocity, you will develop this kind of an instability. Okay, so that is one thing you can actually check within your simulations. If you're getting that, if you're able to get that, is your simulation prediction similar to what the theory says, okay, or experiments? The other thing is the more common one, especially in real life multi-phase flows, wherein, for example, you may have a gas. You may have a gas going at a certain velocity. You may have oil going on at a certain velocity. This could be in oil gas pipelines, and obviously both of them are shearing against each other. And the reason, and of course, it's very similar to the Kelvin-Helmholtz, but there is a big difference. The big difference is that the gas and the liquids, they've got completely different viscosities, and because there is a shear difference there, because there is actually a shear stress difference there. Or the viscosity difference, and that leads to waves, and that is called as the Yi instability. So depending upon the scenario, you can actually simulate a certain problem and then actually check against whether it's coming right or wrong. The other thing is the most common thing within nature, which is the mostly turbulent flows. So if you look at any sort of turbulent flows, you would get a boundary layer. You would get a boundary layer. So I'm sure all of you know what a boundary layer is. So boundary layer is the place where you would have the effect of viscosity coming up, and you will have a velocity profile. Beyond the boundary layer, you will simply have a straight line. Basically, it says that my flow is not really affected by velocity, okay, by viscosity, sorry. So basically, you would have this boundary layer. This is the black line. But this is, if you have a normal laminar boundary layer, this is almost going to be a very smooth line, and it will just go on like that, okay? But then as you turn into turbulence, what you would have is you would have a highly disturbed boundary layer, okay? And the boundary layer completely breaks off as well. You will have a region which is close to the wall, which is highly, that is where all these vortices are being generated, okay? And the reason that is being happening is because if you look at any surface, while it may look very smooth, you may have a pipe, it looks smooth, but if you look at microscopically, or if you look at through if you do an atomic force microscopy over there, then what you would do is you would actually find a lot of roughnesses there, and that roughness is actually instigating these waves. Okay, if your flow velocity is higher, the intensity of these waves is higher, and that disturbs the entire flow, causing turbulence. So that is the Tolmine-Schlichting mode, or the shear mode. There are other velocities, there are other ways in which you can actually instigate changes in flows. So basically, whenever you have a two-phase flow system, you will always see changes in these flows. So when you simulate two-phase flows, if you consider, if you see certain type of a behavior of flow within your simulations, within your CFD simulations, you will always have to question whether the simulation is correct or not. Okay, there are different types of waves. So some waves, as you saw in the previous thing, you may have waves which are actually traveling away. Okay, but in some cases, what you may have is you may have a wave which is actually not just going in one way in the direction of flow, but actually it is spreading throughout the interface. That is called an absolute mode instability. Okay, so there are different ways in which these flow regimes can change, especially if you have multi-phase flows. Okay, especially if you have multi-phase flows. Okay, so and you can have different waves which are competing with each other. I'm going to show you some simulations so that you can really understand. And each of these waves start competing with each other. If you just, so even if you go to Juhu Beach, for example, if you go to Juhu Beach, you will see these waves coming, and you will see that in one direction you will have a wave coming at certain velocity, but somewhere else there is a wave at a different velocity. If you go farther away, you'll find these waves actually interact with each other. Okay, so that is called as transient growth. So that's what we'll also see here. Okay, so just to describe, you may have a system. You may have two types of systems. One is a system which has a supposed steady state. Okay, or the fake steady state, I would say. That means your flow is not being changed throughout. Essentially, if you write down your Navier-Stokes equations, you can actually resolve. You can actually get a steady state solution. It's just like laminar flow in a pipe. That can be easily done using normal Navier-Stokes equations. It's a very simple unidirectional equation, and that's it. Okay. So similarly, for two-phase flows, you can also do that. You can also assume that your interface does not move. That means the gas-liquid interface is going to be stationary. It's almost like a wall, which is wrong anyway. So if you assume that, in that case, you can get a steady state solution. And that so-called steady state solution, what we'll do is we'll just perturb the interface. What we do is you have the steady state, and we're just going to disturb the steady state. You're going to disturb this and see how these waves propagate. If your waves propagate really amplify very well, that is an unstable scenario. So obviously any small wave, any small noise, and that noise could be fluctuations in flow rate, fluctuations in temperature, you name it, any sort of fluctuation, that will just grow. That is called as that is basically highly unstable system. If your disturbance damps down completely, that means that it's a stable system. For example, if you're flowing honey into a pipe, and then you try to disturb the system, all your waves will be damped because honey is so viscous, it will just shut down all kinds of disturbances. Okay, but on the same hand, if you have a pipe full of water and you disturb something, that disturbance can really propagate ahead because there is no viscosity to stop that disturbance. Okay, to dampen that disturbance. So obviously, we are going to look at that thing now. But at the same time, you could have systems where your flow you can never have a steady state. So for example, if you have a flow which is constantly boiling, okay, it's like you make your morning chai, you just take a pan of water and you boil it. Do you ever have steady state in it? No, because your water level keeps decreasing. That's because it's boiling. You've got phase change going on. Okay, but then is the flow stationary? Not at all. In fact, there's a lot of convection currents going on. Okay, so you would have systems without base state as well. So you'd have flows with phase change, you can have evaporation, condensation, and you can also have reactions. So I'm going to show you a few. So basically a stability analysis is what I mentioned is you can have if you have an interface, you just disturb that interface and you will actually see how it grows, how the wave grows. It doesn't tell you anything about the structure of the velocities or anything. Those things can be obtained from numerical simulations. But to validate that, your numerical simulations, you're checking, if I inject a small wave in my numerical simulation, will that grow with the same magnitude? That is what the stability analysis will check for you. Okay, so this is how normally, typically, if you have a highly nonlinear, I mean, initially it will grow as a sine wave. You will have a small sine wave. It may grow further and further, but slowly beyond a certain point, it becomes highly nonlinear, and you will get all these weird structures. Okay. Highly nonlinear. So in my group, we develop a lot of these CFD solvers. One of the things that we have done is basically a two-phase level set solver, which also incorporates a diffuse interface. So I'm going to come to that shortly on how we actually resolve the interface. Okay. So we have used these solvers for stratified flows, falling films, phase change as well. You can have interfacial reactions and contact lines and things like that. So you have different methods for this. You have different things, and all of these solvers are highly resolvable in terms of supercomputers. So essentially, when you're solving a large problem, when you're solving an industrial grade problem, we have to solve it in clusters. So that means that your problem has to be discretized not only in terms of numerically, but also in terms of the processing. Okay, so you would have to use power of many computers to actually solve one problem. Okay, so therefore they are highly parallelized, and we work with the UK's national supercomputer. Okay, and at this point, I would like to pay tribute to one of my ex-supervisors, Professor Spelt from Imperial College. He passed away last year, sadly, but he was one of the main instigators of the solver which we have open sourced. So basically, we also have the PPLS solver, and the other one which we have recently done is the JERIS immerse boundary solver with Rama recently, very recently. So these are experiments. So essentially what is happening here is flow boiling. If you see the first video, you've got a big bubble of gas which is flowing, and as it passes, you've got a Taylor bubble. We call these the Taylor bubbles, and you've got all these events that are happening. So obviously there's a liquid phase, and you've got the bubble which is actually passing away. If you keep increasing your heat flux, as you keep increasing to heat it, what you'll have is you'll have an annulus of gas. You'll have gas flowing in the center, and then liquid film running down on the sides. And you can see these in between, you can see these intermittent waves which are actually flowing all over the place. Okay. And the thing is, if you keep increasing it further, you'll have a mishmash of everything. You would have a highly unregulated or highly turbulent or highly chaotic churn flow. And this is what is reality. Okay. So this is real flows in terms of flow boiling, you will find this in oil and gas channels as well. And if you look at each of these things, you would have several things happening. You would have interface, you've got the gas liquid interface, which actually tears into droplets and it bombards into other places and so on. So all of that should be representable from a CFD simulation. Okay, so these are one of the few slides where you will have some of the equations. So obviously, you guys are much more aware of CFD than I am because you've just done the course. So basically, you would have the mass balance. So this is incompressible. So I'm assuming that it's Newtonian fluid and incompressible fluid. So you have a mass balance that is grad.u equal to 0. This is for all the phases, and this is basically the continuity equation for both the gas and the liquid phase, for all the phases as well. The important thing over here is in the type of treatments which I do, you'll have a single equation. But the way you distinguish between the two phases, that is gas and the liquid, is through the densities and viscosities and surface tensions and things like that. Okay, so this is actually used. So basically, I'm going to show you how I basically calculate my viscosities and densities. The other important thing in any two-phase scenario is you've got the gas phase, you've got the liquid phase, but then you've got this thing in between, that is the interface. And how do you resolve the interface? That is done usually using, there are different ways of doing it. The methods I use typically are the level set function. So the level set function is a function which tells you the distance between, distance from the interface with another phase. So if phi is negative, you may be in the gas phase. If phi is positive, you are in the liquid phase. If phi is equal to 0, you are exactly at the interface. Okay, so that is the distance function. It's actually a distance function. And this is the advection of the distance function. You've got the normal vector, you've got the surface tension, curvature going on. This one, curvature times surface tension gives you the surface forces. Plus, and this is how the densities are regulated as well. So basically, obviously, the density in the liquid phase is higher than the density in the gas phase. And this is how the step is going to be. So here there is, if it is air and water, the density of over here is 1,000 kilograms per meter cube. Over here is approximately 1. Okay, so there is a big jump across the interface. And that jump is basically characterized by this function. Okay. So phi also acts like, it's almost like a pseudo volume fraction, but I wouldn't really go, I don't really call a volume fraction, but it acts something like that. Similarly, the viscosity would also change because viscosity of the liquid is going to be very, very different from the viscosity of the gas. Okay, so, and that is the big sharp change at the interface. There is another way of dealing with this as well. So that is one method where you have the level set function. The other thing is you assume that, I mean, the thing is, if you look at the interface closely, very closely, you will see that it may have a certain thickness. Okay, it may have a certain thickness, and based on the thickness, that interface can move. Okay, so based on that, this is called as a Cahn-Hilliard approach. Cahn-Hilliard approach has C, which is the volume fraction. So essentially, if volume fraction is 1, you're in the liquid phase. If volume fraction is 0, you're in the gas phase. Okay, that's how it is. And then, but on the interface, you say that the interface is slightly thick. It is thick, and it's not very thick. Obviously, you don't have thick interfaces. It has certain finite thickness based on the discretization. So if you have a grid size of delta x, then that is 0.5 times delta x. That's how the thickness is defined. Okay, and everything else, all of these things are evaluated from the interfacial thermodynamics. So basically, surface thermodynamics regulate how the interface moves. So essentially, all of these things are directly coming from physics. Okay, directly coming from physics. So there is no assumptions that is involved. The only thing that you have done is basically used mass balance, that is the continuity equation, Newton's second law, which is the equation of motion, and then you've got this interface treatment based on van der Waals thermodynamics. That's it. Okay, so there are no assumptions there. The only other assumption, yes, there is one assumption, is that you've got this jump, that is density in the liquid phase is extremely different than the density of the gas phase. So there is this jump across the interface, similar to that of the viscosity. So this is how your densities and viscosities are represented. So this is just an example. An example here is basically looking at, you've got liquid phase at the bottom, you've got the gas phase at the top. I've just called as mu T and mu B, upper layer and lower layer. And obviously what I do is so as I mentioned, I want to really understand whether my numerical simulation is actually representing reality. Okay, so what I do is I put a force, I put basically a kind of a perturbation. Okay, I just give a kind of a small wiggle. It's a sine function. I give a small sine function very close to this inlet. Okay, and what I'm going to do is I'm going to see how these evolve. So as you can see that these waves, they initially start at the same point, but then they start competing with each other. In some cases, they will actually start collaborating with each other, that is joining with each other and forming more and more ligaments. So this is how your flow can occur. And this is from our own solver. So you can define a Reynolds number. And obviously the important thing over here is you've got surface tension. So you have a capillary number as well. Okay, so the objective is to see. So if I can show you some movies. So here you've got the, I've initiated that little wiggle, that kind of a small disturbance. And then you quickly see that you've got this snaking formation. You've got while we start at the same point, each point of this fluid is behaving in a very different way. Okay, and you'll find that one guy grows very rapidly. This forms a kind of a tongue or a ligament. This guy is a bit late, but slowly this will also catch up, and you get all kinds of very complex dynamics. So obviously you will have very complex interaction between the waves. We have studied this very carefully as well on how these waves interact with each other. Okay, and we find that they're actually, so this is the pink line is what the theory represents. This is how the waves grow. This is where the stability analysis comes in. So this is how the waves grow. This is showing that this is basically amplitude versus time. Okay, so this is how the waves grow. And if you look at all our other dots, if this is the straight line, and the straight pink line is the theory, that is the theoretical growth rate. And if you look at our DNS or CFD simulation, they're very, very close. And after a point, it becomes, I mean, the waves don't grow permanently. You've got gravity, which is pulling everything. So obviously at certain point, beyond a certain point, these waves will collapse, okay? And that's what and at that point, you're not really comparing with theory anymore. This becomes highly nonlinear at that point, okay? So we compare it with both the case of the waves which are growing in the streamwise direction, that is in the direction of flow, but also perpendicular to the direction of flow. So we compare that. We also seen collaborations of these waves. In this case, if you remember your previous video, I don't want to show it again because it'll probably slow down my PC. So you'll see that there were two of these waves which are actually combining with each other and then doing it. So when we do an analysis, you can also see that there is actually a combination between two waves. Alpha is basically the wave number, that is the wavelength of the wave. So there are two particular wavelengths which actually collaborate to form another wave. Okay, so we can also see that. So whatever we do in terms of DNS, we are comparing against theory, also against experiment. I'm going to come to that soon. So you can have all kinds of things. If you keep increasing surface tension, you will get ligaments. You will get these ligaments. You can see that fine threads that are coming up and breaking up into droplets. So this is basically what you get if you increase surface tension. If you increase Reynolds number, what you will get is you'll get a highly turbulent chaos here. Okay, so if you look at this, it looks a very, very complex picture. It's almost like these waves as they slush, as they hit a kind of something somewhere, as they hit a boulder or something. Okay, so there you've got a complex set of dynamics that are happening here. Okay, we can also compare. We can also study what happens. How does the curvature of the interface change? So this is space-time. So this is this is the position where you instigated your wiggle, where you instigated the disturbance, and this is showing the curvature. So obviously, if it's a flat interface, you don't have any curvature. Everything is zero. Okay, you don't have any curvature, or you've got infinite curvature. This is 1 over curvature, I think. Okay, so you have nothing. But then the moment you instigate that wave, you will have a finite curvature, and you'll see that some of these waves are collaborating with each other. You can see that these two waves have merged with each other to form a bigger wave, and so on and so forth. So it's basically a lot of analysis which goes on after your simulations have shown results. Okay, so this is one of the things. So the other example I can give you is in chemical engineering, you've got distillation and absorption towers. So obviously these are there. I'm a chemical engineer. It's the bread and butter of chemical engineering. People design these absorption and distillation towers for refineries, for chemicals, for you name it, for everything. For purification, you need to have these things. Okay, and obviously if you look at these distillation towers, you will have that these are huge columns. I mean, if you go to Rasayani, or if you go towards all these chemical plants, you'll see these big columns. And these columns, if you'll take a section of that columns, you will see that you will have a structured packing. You've got these columns have stuffings in it, and these stuffings are basically structured packings. If you look at these stuffings properly, you will actually see that there are two surfaces through which gas flows upwards and liquid rains downwards. So this is pure chemical engineering. So you got countercurrent flow here. Okay, and the idea is that if you want to have very good quality refinery, if you want to have very good quality refining going on, then you need to make sure that you have good you've got good availability of heat and mass transfer through the interface. Okay, and so these particular surfaces, these structured packing surfaces, provide you with that surface, and that helps you to really enhance your activity, enhance your efficiencies of these columns. Okay, so the idea is basically to understand how the flow occurs and what we can do to design this better, what we can do to design the surface better. So if you understand the flow here, you will be probably able to design the structured packings much better. Okay, so this is again a kind of a section of the structured packing. What you have is you've got liquid which is going down here in this towards the left wall. This is the interface. So initially, I'm assuming a small, and if you see carefully, there is actually a small wiggle which is being put here. And then you've got gas which is running upstairs, which is going upwards. Now, if you talk to people in Reliance who operate these refineries, they would say that they will never operate they will operate their columns which is close to the loading point or beyond the loading point. That is when you're almost having maximum, you're operating at your maximum capacity, because at maximum capacity, you're actually producing so much of waves in the film that it enhances heat and mass transfer. Okay, they always operate at a higher value. They don't operate at the flooding limit, but they operate at the loading limit. So this is how it looks like. So basically, at that point, what you have is you've got the liquid which is going down. Remember that liquid is going down, but any wave, you see that the wave is not going down. Actually, it's going upwards. It is going against gravity. This is basically called, and any wave which is produced here, yeah, some of the waves are going downwards, but there is a little bit of wave which is going upwards because of upward pushing of gas. This is called as an absolute instability. And this is what happens when you are in flooding or when you are close to the loading point or slightly above loading point. So you can again analyze your results. You can check against theory. Whether your equations or whether your simulations or CFD simulations are okay. We can see that you've got a very good growth rate in comparison to that of the theory. So this is the dotted line is the spatiotemporal Sommerfeld analysis. So that is the stability analysis. And basically you've got the DNS, that is the CFD simulations here. Okay, so you can obviously, we have published this, so you can have a look at if you're interested in all of this work. Now what we'll do is we'll look at a case which is very, very topical, which is about systems without base state. That is, systems that are actually evaporating with time. Okay, so this is another example I'm going to talk to you about. So over here, this is my colleague's experiment. I'm going to, hopefully this will come up soon. So you see this is a methanol droplet. So it's a droplet of methanol placed on a surface and it's evaporating. Okay, it's evaporating. And what my colleague is doing is he's putting an infrared camera on top of it. So you can see that this is a thermal signature, but the thermal signature is not constant. It's actually showing that you've got these waves which are going all over the place. Okay, so why is this important to know? Basically, if you want to cool anything, especially your computers, your mobile phones or whatever, you need, normally all of your computers will have fans in it. But what we know definitely is fan is not a great cooler. I mean, it doesn't really remove all of the heat. I mean, if you touch your computer towards the side where the fan is, you will see a lot of hot air coming out. But we know that 40% of that air doesn't do anything. It doesn't cool it. So we are investigating new ways to cool these microelectronic devices using refrigerant type of fluids. Okay, so when you have a refrigerant, you've got phase change mass flux, phase change heat flux, which is much more efficient than single phase sensible heat flux. So and just how your refrigerator works, this is going to be much more efficient cooling. And we have tried this in both Earth as well as space environments. The reason this is important is because nowadays all of our lives are basically data. Okay, all of our lives are stored as data, and these data could be stored in data centers. Some of these are obviously stored, some of these are completely interacted with the satellites and things like that. Okay, so if you want to make sure that if you want to safeguard your data, it's important that your hardware is safe. Okay, so all data centers use enormous amounts of money to cool them, to keep the data centers cool. That's why most of the things are there in air conditioning environments and things like that. And they also know that it's not very efficient. Okay, so one way to possibly cool that better is by using refrigerants. So we have devised several systems on that, and Fujitsu has done a lot of experiments as well. Okay, and in fact, yesterday I was in chat with the European Space Agency, and we are going to send an experiment in the International Space Station to check how it works there. Okay, now, so in this case, it's the evaporation which causes these instabilities, these kinds of events. And if we understand the phase change phenomena better, if we understand the fluid mechanics better there and the heat transfer better there, this is multi-phase, of course. So we may be able to design your chips or whatever cooling systems much more accurately. Okay, so we could see, we have done some analysis, and you can see that this is on the right side. You can see that we could predict some kind of these thermal patterns in that way, but that is purely through stability analysis. Okay, now what we're going to do now is do complete simulation. So what we have is, if you look at any sort of droplets anywhere, they're never spherical. Okay, even if you have a spherical droplet, like what my colleague's experiment showed, or a hemispherical droplet, you will have three-dimensional phenomena occurring all over the place. So if you look at the top image, this is basically the snapshot from what I've showed you. But then the bottom image is the droplet of blood, which is evaporating. So as it evaporates, blood is a highly complex fluid. It has all kinds of weird things in it. So it actually leaves out patterns in that way. Okay, and obviously, and there is nothing symmetric about these patterns. You don't have an axis symmetry. You don't have anything. So basically, it's a completely three-dimensional phenomena. Okay, you may initially start off with symmetry conditions, but soon the symmetry is destroyed because of the fluid dynamics going on. So again, what we do is we simply take a drop. We put that drop on a surface which is heated over here. This is numerics, yeah. Surface which is heated, and this then evaporates. So basically, you can see that you will get all kinds of rich dimensionless groups coming up. This is the typical set of equations. I'm just repeating some of these equations here. You've got the Kahn-Hilliard equation, which is defining how the droplet how the droplet interface will interact, will be simulated. You'll have the continuity equation. You have the the energy equation. You have the momentum. The energy equation is there. This is coupled to the momentum equation. You've got surface tension. You've got the tangential component of surface tension, and so on. And then you've got the species equation. Now, the species equation is because anything you evaporate. So if you evaporate methanol, or if you evaporate your tea as you make your coffee, or as you make your chai in the morning, the vapor gets contaminated. The vapor has the other component going into it. Okay. So if you have surrounding air, this is contaminated by vapor methanol. So we need to really account for that as well. So this is, whenever you have phase change, you would have species equation in the gas phase. You would have evaporative flux. Okay. Defined by that, you have got the mass flux. That is because there is some amount of liquid going into the gas. So basically you're depleting the liquid, but enhancing the gas. So that has to be accounted for. Plus your interface, this is the interface, it's going to change with time. So it's going to actually come down with time. So even that is represented now. Okay. And then we have a very simple phase change model based on evaporation. So if you're a chemical engineer, you will easily understand that this is basically Raoult's law. Okay, so you got a phase change model completely based on equilibrium thermodynamics, vapor liquid equilibrium thermodynamics. Okay, so and basically the important thing is this drop is placed on a substrate, on a surface. Okay, now usually in CFD, walls have a wall boundary condition. We say that whatever is the velocity of the wall, it's going to be the same velocity as that of the liquid or whatever is around it. Okay, so that is the wall boundary condition. So if I put a wall boundary condition, that is no slip wall, that means that there is zero velocity. That means that the interface is also pinned. It's basically will not move here and there. No, because that will refute the boundary condition, because it means that whatever is touching the boundary will have the same velocity as that of the boundary. So if the velocity is zero, it's not going to move simply. Okay, but then, because this is a Kahn-Hilliard model and there is the mobility term, this is the van der Waals mobility term here, you will find that, I'm going to show you some experiments as well, wherein actually it shows different. If you put a drop on the surface, and as you, it's very simple. Just take your tawa, okay, as you try to prepare dosa or chapati or whatever, heat it up like mad, okay, and just put a droplet of oil. Does the oil remain stationary? No, it actually starts moving. It's not slip, but it actually moves. That's because of the thermodynamics. Okay, so basically this is what dictates the thermodynamics, the M parameter. So if there is a motion, what it means is that the energy within the droplet, there is some sort of an imbalance between energy within the droplet and energy outside. So to balance that, this guy would actually move up here and there. Okay, so basically that is what is defined by the including that of the interface. This is what is happening at the contact line. That is where your the interface touches the solid. Okay, so this is what is done. This is the typical formulation. We also did a lot of checks in terms of, I mean, these slides will be available, don't worry. So we also did a lot of checks. So this is the first check. So this is just a two-dimensional. This is a wrong droplet. This is a fake droplet, I would say, fake news. But this is just to check whether our droplet or the equations are behaving properly. Okay, we could get a nice set of temperature profiles, both within the gas as well as in the liquid phase. This is the evaporation flux as it happens. You have the velocity field driven by surface tension within the droplet as well. Okay, we compared it with experiments. Okay, now we are doing a full 3D simulations. Yeah, we compared it with experiments. So you've got a copper substrate. So you've got a little bit of a droplet here, and then as what you would happen, what my students saw is that most of the time the droplet remain almost fixed. If you see this radius, the radius does not change with the time much. So that means that the droplet is fixed to this, but the only thing is obviously its contact angle has changed because it's actually depleting. It's evaporating as things happen. Okay, so we compared that. So we compared this is the blue is the experiment. This is a simulation. We are very, very close. So which really gives us confidence in terms of our DNS model. Okay, we also compared it against literature where the droplets actually move as they evaporate. Okay, so we have also compared with that. That also looks fine. Okay, but when you do the simulations, this is fascinating. When you do the simulations, what you will find is basically that initially it almost looks symmetric. So people will say, oh, why did you not use symmetry? तुम लोग ने symmetry boundary condition क्यों नहीं use किया? So and the thing is, the reason is, wait for some time and you will immediately see these azimuthal currents which are developing within the droplet. And if you had a symmetry simulation, you will never see this. You will never see this because symmetry means whatever is happening on this wall is going to happen in the same way. But obviously, if there is flow entering that wall, symmetry will destroy that. Okay, so you need to be very, very sure in terms of when you use your boundary conditions. Okay, so basically, if you have this kind of a vertical motion within the droplet, then you should never have a symmetry. So there is breakage of symmetry. So you've got azimuthal currents, which is going on. And this won the prize, actually. So this is the experiment. So this is a very, very weird looking droplet. And this is from the top experiment. So this is basically showing temperatures. And you can see these cooling, cold vorticular structures. We compared it with our DNS as well, that is CFD as well. And we see that we have almost similar, somewhat similar patches as well. So again, this is all published. So this is you can see these papers. We have also done a lot of other work in terms of what happens if you, for example, if you look at refrigerants. Refrigerants are not simple fluids; they're very complex fluids. Sometimes they're combinations of different fluids as well. I mean, in this case, what we do is we put water and methanol, and you can see that the moment, and this is on a hot substrate. So as you put the droplet, it actually spreads rapidly and then retracts back. So we are also doing simulations for that. Okay, we are also doing simulations for that. So that is also published, and we also did some work if you have salt in it and things like that. Simultaneously, as I mentioned, with Rama, we also developed this the solid fluid solver. So wherein you've got two phase systems. So one of the phase is obviously solids, and the other one is liquid. And actually, and the idea is to understand how these solids tumble. across in the domain. Okay, so this is how this has also been published. So one of the things I would say as I finish the simulation, as I finish my talk for 45 minutes, is that you will have, so whenever you have phase change, you will have remarkable phase segregation behavior. Plus, at the same time, you would also have this kind of vorticular currents. Okay, they regulate. So you've got countercurrent, counter-rotating vortices that can regulate heat transfer. Obviously, understanding waves in horizontal or vertical two-phase flows is very, very important for both design as well as for understanding the development of your process. Okay, so that's extremely important there. There's also so we've written a book chapter completely on this, so you can also have a look at that. But the important thing is, whenever you do any CFD, you have to make sure that you validate it. Okay, and especially for two-phase flows, especially if you have multi-phase flows, you would have to validate it against very powerful methods, experiments, very good experiments, and something like theoretical analyses like stability analysis. Okay, so obviously CFD will give you capability to examine all of these flows in unprecedented detail. It's a very, very powerful tool to understand, but you need to know what you're looking for, and you need to know that what you're getting out from your computers is actually correct. Okay, is actually correct. So that is where a lot of time is spent in terms of checking whether your simulations are correct. So with this, I would like to stop and thank you for your attention, and I open the floor for questions.
Thank you, Professor Valluri, for that fantastic presentation. Very interesting indeed. The floor is now open for questions. So please feel free to ask any questions that you may have. You can even post it in the chat window, or you can unmute yourself and ask.
So I also want to introduce Professor Janani. She's the one who leads this CFD and open form effort at IIT Bombay.
Right.
And Janani is in the audience.
Yes, sir, I'm here.
Janani, you want to say hello to Prashant?
Yes.
You have a question, you can go ahead with your questions. That's also okay.
Yes. So it's a pleasure that you were able to make it to come and see us and give us this very informative.
It's an honor. Thank you, Janani. Thank you.
Yeah, thanks for coming in. And actually there was a lot of requests for multi-phase flows, which was not part of this workshop initially planned. And we did have a session prior where some basics were handled, and it is actually very fitting that you were able to show the expanse of applications that is possible. So I think thank you very much for coming in and talking to the audience here.
Most welcome. It's a pleasure. It's always a pleasure.
Yes. So I think I should open up the thing. There's a comment that it's an excellent presentation, so I don't have.
Thank you, everyone.
Yeah. So people, please, this is an opportunity that you don't want to miss. So can you please ask Professor Valluri any questions?
Hi, good afternoon. It's Adik Majumdar here.
Yeah.
Hello. So my question is in that methanol droplet evaporation experiment. My question is, have you observed any kind of fractals, development of any fractals or shape?
Yeah, actually we have it. We don't see fractals because it's very difficult to identify them, but I can probably, I'll see if I can share a movie with you wherein we actually see extremely complex dynamics. Just give me 2 seconds. I'm going to show you, probably here is.
Yes, okay, sir.
I'm just going to show you some examples of what happens if you have, what happens in the experiment. I'm just going to share my screen. Give me 2 seconds. Oh, yeah. So this is another, you see, this is what happens. So this is how you can see these, you can see this experiment. This is ethanol water. As it evaporates, you can see a lot of dynamics going on. And this is an IR image. So ethanol, so water is opaque to IR. So that is basically the black region, I would say. And ethanol is not as opaque to IR. So that is the white region. So you can see that there's a lot of activity that is going on in terms of this. So what we found is we have done a lot of analysis on this. what we found that there is actually segregation of material that is going on. So obviously ethanol being less volatile, ethanol being more volatile, it's pushed towards the sides and that evaporates faster. So that actually is pumped out to the interface, and that's where evaporations are going on. But at the same time, in this case, this was a very specific experiment where we held the droplet, but in reality, as I showed you in the other video, your ethanol, the moment you have an ethanol water droplet, it spreads rapidly. So it's very, very difficult to actually, in this case, we forcibly fix the droplet to understand what is going on inside. But we know that you've got a lot of these complex events that are going on. So they're not really fractal-like, but, and we have analyzed this, so they are not fractals, but they look quite chaotic.
Oh, okay, sir.
So I have a question. How much of computational background that people come with when they join your group, and how much do they develop? Because these are solved with standard solvers, or special purpose solvers are written and used?
Yeah, so good question. So basically, all of my students, when they start for PhD, they possibly may not have much of CFD background at all. They actually learn through the process. And then so most of our work, we actually start them on commercial solvers just so that they get the hang of it. But then they immediately follow on with our own solvers. So we have our own developed solvers. So, and there is a lot of effort in developing that. So we make sure that there is a lot of support given to them in terms of training them into the solvers, plus at the same time looking at the code. Actually, one of the biggest, I myself, when I look at someone else's code, it's such a nightmare. So we do give a lot of time for them to really learn these solvers. So it does take time. So I don't expect my students to have a very good understanding of the the only thing I would require them is the understanding of the basic fluid mechanics and the basic thermodynamics and basic heat and mass transfer. And some interest in terms of, obviously I gauge that, are you interested in code development? That is always my question. If they say no, then it's a difficult thing within my group, of course, but because they would always do some code development.
Just a related question. So how much are you adopting the open form software?
So I'll tell you, so many of my students, they actually, when I say that they get started on some commercial software, it includes OpenFOAM as well. OpenFOAM is not commercial, but so it's just for them. If they've not really done CFD at all, I say do whatever you can. Just pick up any software you would want. Just look at basic questions. Just make sure, but plausible questions. So I ask them to solve for a two-phase flow or a step, for example, or basically just two-phase flow in a system, or even a single-phase flow. Just basic examples. And then I try to ask them questions so that they actually develop that method of post-processing and analyzing results, because that also takes a lot of time, as you know. So and basically asking them to identify mistakes within their work. So I use that method. So I don't particularly use OpenFOAM for my own work, but my students use OpenFOAM for their own learning or things. Yeah.
Does the audience have any questions? Anybody, any other participants?
I think we have a question, sir, regarding the language you are using for this equation solving.
Okay. Good question. So most of our solvers, I'm a prehistoric dinosaur. So most of my solvers are in Fortran 77 or Fortran 90. But some of my students, they have developed stuff in Python as well. But most of the solvers which I showed you today, they are either Fortran 77, Fortran, or maybe at some point C++, but nothing more than that. And the operating system there. So yeah, we have done several things here in terms of operating systems. So we use our supercomputing system. We use our supercomputing cluster. So essentially, it's a kind of a Cray system. But we have implemented our solvers in other supercomputing systems. So even in India, this has been employed in, I don't know which cluster, but was it in IISc Bangalore, or was it in TIFR Bangalore? One of these. So it works fine. So as far as these solvers are, they work fine in whatever clusters. We have tested them in the US as well. So I think they work. I mean, as long as it is a Linux cluster, as long as it's a basic cluster with basic, with enough Fortran compilers, I'm sure this would work. Any further questions? I would like to hear how zero gravity fluid behaviors. Okay, so good question. So one of the things that we actually have done is we look at, within my group, we also look at microgravity events. So we do, so in terms of solving the system, it's very simple in the sense like the only thing that is now missing is the gravity, is the body force term in your governing equations. But the important thing that you need to make sure is your solver is able to handle the density ratios and the viscosity ratios properly. So it just means that we need to have a very good numerical scheme to solve these equations. So we use a Vino convection scheme for most of our equations there. So especially the nonlinear equations. So as long as that is there, then you can easily work on zero gravity behavior. I'm not sure if that answers your question. There's another question on artificial intelligence based approach. People have used, so my colleagues in Nottingham, they use, or in Southampton, they have used machine learning very recently to understand the behavior of fish, how they flow and things like that. But so there is some work there, and also to understand turbulence, possibly machine learning is being used. I'm not sure about the artificial intelligence based approach because I don't understand it much. But definitely machine learning, it has been used. I mean, with varied success. I mean, machine learning is just a big phrase word nowadays. So yeah. Have you done in medical sciences? Yes. So one of my PhD students, well, I have graduated a couple of PhD students who work on the flows in the brain. So we look at neural network, we look at brain cooling. So we develop our own solvers for that as well. In fact, I can I can show you. I'll just share my screen. So if you look at this vapor. Vapor is vascular porous model for simulating biological temperature. So this is what we have developed. It's a very, very simple tool in MATLAB to actually understand the flows within the brain and how the temperature is regulated within the brain. This is basically for people with trauma, extreme cerebral trauma, people who have undergone accidents, or people who are, I mean, especially also neonatal births, which are very difficult. They have to be cooled. The babies have to be cooled. People have to be cooled. But then we want to understand the effect of cooling in the brain. Cooling is good because it helps prevent some inflammation. There is a lot of evidence of that, medical evidence. But we wanted to understand what is the fundamental principles by which cooling can occur within the brain. So there is also a paper which has been published, so you can have a look. There is another student of mine who works in terms of flows in the lungs. So I do work with some level of medical, in medical science, people with neurology and people in respiratory systems. So I do work with them. Can any water treatment process be designed? That's a very large question. It depends upon what you're looking for. If you're looking for membrane separations, obviously, I mean, all of the CFD and all of these methods, continuum-based methods, they are only valid in the continuum range. So that means that your system size or your process size should be more than at least 10 microns. Okay. Obviously, when you look at membrane systems, you're getting into atomistic and molecular levels, and those you cannot solve using these methods. You need to have multi-scale methods. You need to couple it with MD and LBM, lattice-Boltzmann, and things like that. So your answer of course, there are other water treatment processes which can be simulated, the broad behavior. But I think if you want to really look at desalination or things like that, they cannot be done using these methods. You need to have very, very specific methods for that.
Hello, sir. One more.
Yeah.
Yes, sir. In one of the slides, you have shown one word boiling image.
Yeah.
Droplet.
Yes.
There was I see some spiral kind of thing. What is that?
Spiral. Oh, these are streamlines. So do you mean that? I'll just share my screen again.
Is it as an internal flow that is happening in the droplet?
Yeah, that is the internal flow in the droplet. I think you're talking about this, right? Can you see my screen?
Yes, we can see the screen. Dr. Majumdar, is this what you?
I can see.
Yeah. So this is the internal flow within the droplet. Yeah, these are the vorticular currents, vortex currents that are going around in the droplet. And these are basically streamlines.
Okay. Magnificent.
Okay. I'm doing photocatalytic reaction. Can I design spreading? I don't know whether you can do it using this. You can simulate reactions. There's no problem with that. But I'm not sure whether you can do spreading of UV light. You need to have other methods for doing that, because that is beyond the realm of fluid mechanics here. So beyond the realm, I mean, the thing is, for example, people have combined flows with ultrasound and things like that, and they've done sono fluid mechanics simulations and things like that. So you may want to do, you may have to look at other methods of simulating light, spreading of UV light and other things. So definitely not, you can simulate reactions using flows. There's no problem with that. So any other software other than FlowPack? I'm not sure about the FlowPack. I think all of these software, they solve the same set of equations mostly. So as long as the physics are correct, they should be fine. Azimuthal currents are there only in droplets, or do we have? You will have these currents established almost everywhere. But definitely we were looking into droplets because there was a lot of work done using symmetrical droplets, which is a weird thing. So we wanted to show that you can't have symmetry boundary condition within a droplet. That's what we wanted to show. You will get azimuthal currents in other systems. Of course, as you have, for example, even if you take a pan of water and boil it, you won't have, there is no symmetry there. You will have things happening at all the points. So you would have azimuthal currents as well. The strength of the azimuthal currents is also important. The strength of the azimuthal currents may be low, but they exist. Is it possible to, noise is acoustics, right? So no, you can't use CFD, but you need to use parallel methods to actually talk to CFD and understand. Yes, we can use the same approach. So we have done a lot of these cardiovascular simulations. So yes, that can be done, Mahalakshmi.
Okay. I think thank you very much. I would like to formally thank Professor Prashant Valluri for this fantastic presentation. And I know I speak for everyone when we say we've immensely benefited from this.
Thank you so much.
Kannan sir had to leave for another meeting, so I stepped in. And yeah, thanks again. It was a pleasure having you at such a short notice and given the time difference. So thanks once again.
Thank you so much. Thank you so much. Thank you so much, everyone. Thank you, Janni.
Have a good day. Thank you.
Bye.
Bye. Bye.